good morning, good afternoon, good evening. Thank you all so much for joining us. I'm delighted to welcome you to today's Science Talk. For those of you who are joining us for the first time, welcome. The Science Talks are our weekly series that showcases the exciting research of UNU-INWEH, and I'm very pleased to share that all of our Science Talks from the 2024 series, hosted by Professor Grace Oluwasanya, as well as the 2025 series are available online at our website at www.inweh.science-talks with an S at the end. Today's talk, like all others, will be recorded, and the recording will be made available on our YouTube channel and website after the talk. I'd like to remind you that we'll conclude with an interactive question and answer session, so please use the Q&A box to put your questions in the chat, and I will be sure to read them out to our speaker today. The topic of today's talk is urban flood forecasting and community-based risk mitigation, integrated approaches from Mumbai to the Caribbean and New York City. And our speaker is Professor Reza Khanbilvardi. He's the executive co-director of the UNU Hub on Remote Sensing and Sustainable Innovations for Resilient Urban Systems, or RCERS, the new UNU Hub at CCNY. And he's also the NOAA Chair Professor of Civil Engineering, CUNY Crest Institute. His research focuses on applying remote sensing to hydroclimate studies, and water resources management. He's made significant contributions to flash flooding, assessing climate change impacts on water systems, snow water equivalent estimation, and surface water hydraulics. He's authored over 220 national and international research papers and has contributed as an editor to 5 books. Professor Khanbilvardi has a long-standing record of impactful leadership. He was the founding director of 2 NOAA Cooperative Science Centers, CREST from 2001 to 2016, and CESSRST from 2016 to 2021. Advanced education and research in environmental sciences. In addition to his UNU role, Professor Khanbilvardi is the executive director of the Earth System Sciences Environmental Engineering Program at CCNY, and the founder and executive director of the CUNY Remote Sensing of the Earth, the CUNY Crest Institute. And with that, without further ado, I'm going to turn it over to you, Professor Khanbilvardi.
Thank you very much, Mariam, and thank you for everybody who is, I can see their picture around the desk in Canada and those that they are online. As Mariam was saying that today I want to focus on the urban flooding issues that are one of the dominant issues in large populated, densely populated areas, whether we're looking at New York City or India or Caribbeans, the issues are the same, and we're trying to, with our research activity, try to find a way that we can help the community, both local community as well as governmental agencies, to be able to prepare for the flood, which is the result of a lot of these climate changes also. So with that, I am going to
Reza, can you hear us? Reza?
Okay, I'm sorry, I forgot to unmute myself.
Yeah, you're good now.
You are good now. Okay, let me go back. Yeah, let me start again. Go back to my... Okay. Good morning to everybody around the table in Canada, as well as people online. As Mariam was talking about, I mean, we are focusing on a number of issues on related to climate change and climate impact. In particular, one of the areas that my research team is very focused on it is looking at the urban environment, largely areas that they are densely populated, and they are very vulnerable to floods, and how we can help communities as well as governmental agencies to deal with the impact of the floods on their communities. So we're talking about an integrated approach, and some of the examples of the research areas that we are focusing is from India and Mumbai, and also from Caribbean, Puerto Rico, and U.S. Virgin Island, as well as New York City. Uh, in terms of urban flooding, as we all know, urban flooding is a very growing challenges, not only in New York City, many part of the countries. And with climate change and rapid urbanization, this is going to get even worse. So there is going to be more frequent floods and more intense floods. As a result, the community are going to be severely impacted. So the work that we are doing here at City College, and my colleagues are and my research team is really focusing on integrated multi-regional approach to address the risk associated with the floods that are coming up in large urban areas. We are integrating a number of different approaches. One is AI-based forecasting system. The other one, ingestion of the satellite data. We are one of the places in Northeast. We probably are the only one that has both polar orbiting as well as geostationary satellites receiving a station. So we use a lot of satellite data, and we also looking at the high resolution flood risk mapping to map so the community and the industry as well as the agency can use. And we are also not only looking at forecasting, we try to find a solution to it too. And most of those solutions, we're hoping that they be nature-based solution for those. So we're going to try to build a better resilience community, and we're trying to provide tools for that. So the objective of this seminar today, presentation today, is showing the development of the AI-based urban flood forecasting system, which would be real-time predictions using a number of elements: hydrometeorological, topographical, and remote sensing data, and also enhance the early warning capabilities that might be related to communities, especially in New York City. And we generate high resolution inlet flood risk map also, which we integrated the duration and depth duration frequency curves for different terrain in Puerto Rico and U.S. Virgin Islands. And we try to find a community-based, nature-based flood mitigation strategy for it. And we try to our research to be scalable and transferable to other communities, the other geographical locations that they might have the same issues. My first example is going to be in Bombay, India, that we are developing an AI-driven forecasting and modeling. And in this one, the main objective is to develop a data-driven framework for flood risk mapping. And we use machine learning techniques to ingest a lot of remote sensing data, and we use the SAR imagery data and topographic and meteorological data into a flood prediction and management tool for Mumbai, India. And the reason for that we do this one because there is agencies are in India that they like to see this prediction and this forecasting so they can do this better disaster management strategy there. So we try to utilize SAR, which is synthetic aperture radar, and also a lot of the other data detection techniques. And the satellite that we use in that one is Sentinel-1 satellite data that we use to come up with a better accuracy, and also it penetrates through the cloud, so you have a you try to overcome the limitation by the cloud coverage. And also created a dynamic flood risk map for disaster management. Um, Here is on the right side, you see a map of the Bombay, and it is a frequent and severe flooding events there disrupt a lot of lives and infrastructure. And also there is a major rapid urbanization and inadequate drainage system to take care of the problems. And 2005 floods and 2017 heavy rainfall showed the urgent need for such the techniques or predictive models for a better management tools. Between 2005 and 2015, there were about 3,000 life lost during the floods and $2.5 billion damages that caused. And Bombay is ranked fifth in the world with respect to flooding issue and the annual loss of about $284 million that is estimated they spend on flood damages. So the issue is very severe, and we try to help in any way scientifically to help them to manage it better. The methodology that we use for India, I mean, on data, we have three sources of data that you can see here. One is the rainfall data on the data set that we use. The other one is the DEM digital elevation models data that we use, and the other one is satellite data that we use. So we try to combine all these three sources of data, and as you can see from this chart, you can see the sources and the time period that those data have become available to us, and the resolution of the data. And some of them are daily, some of them are weekly, and there are also 10-meter resolutions for different part of it, and the availability of the event that we have. Um, if I want to break it down into, we use the data, rainfall data that we have obtained from the governmental agencies there, and we clean the data, we extracted the data, and we try to compare it with the satellite data to see which one are corresponding to those. And then on the digital elevation model, we use a 10-meter resolution sampling and try to align those with the satellite data and graded slope. And this, the map on the right side shows the slope, the degree of the slope that exists in Bombay. And in terms of the satellite data, we pre-process the data using different computational techniques that we have, the Python and the Snap. And then we try to come up with the RGB composite map, and then we identify the flood area. And if you can see, this is one of the shots of 2017, August 29, is the white area on shows the flooded area of the Bombay, and this is the map of the Bombay. So we can identify the flood zones on a 10-meter resolution, which is very high, and compare that to the rainfall data that we have obtained from the rain gauges. So after all these three set of data that we do, we do data preparation. We use machine learning models, but before that one, we have to prepare the data, and then we use three different machine learning techniques: logistics regression, GBM classification, and also GBM regression. And then we use analysis, comparative analysis. We do a lot of statistical analysis to find the accuracy, precision, and the error that are associated with these models to see which one fits better for the situation in Bombay. This is a snap of the testing confusion metrics, which basically says the flooded area on the right side is the true labor. So if it was flooded And if we predict on the horizontal one is the prediction that our models does. So is, for example, here is 9.10 10 power 6. We predicted it should be flooding, and it was flooded. And then on the left side, we predicted, the model predicted it's not flooded, but it was flooded. So if you look at this one, the yellow ones are the good ones, and the light blue ones are the good ones that matches prediction versus what it happened in the field. And as you see, there is still a lot of area that they are, we predicted to be flooded, but it was not flooded. So those are some of the errors that are exist right now. So in terms of um, looking at statistical interpretation of those results, there are logistic regression and GBM classification. And as you can see on the right side is the value of the F1 score. And these are the accuracy, precision, recall, and F1 score. You see the top one, and the number closer to 1 is the best one, which means it's perfect. 0 is very bad. So both regression, logistic, as well as GBM classification, they are in the middle range. With the advantage goes to GBM classification, which is at minimum is zero point 0.6 and it's going up to 0.78. And so we concluded that the GBM classification are significantly higher recall values and F1 score. So it's much better performance and prediction techniques than other ones that are less. Um, the right side is the residual plots that also shows the mean square error and the R square. And as you can see, there are a linear residual, which suggests there are some under fitting in it. But the main conclusion was that we found that in using the GBM classification was the best of all of those models, that a slope is one of the most important criteria in floods in Bombay, and rainfall is second. So in terms of priority of things, so one is the slope, the other one is rainfall. There are other elements like the catchment basin things, but these are the two main cause of the floodings, contributing to flooding. So in terms of conclusion, that one, again, machine learning can be used. GBM classification has shown strong values, and regression was the poorer one. And where we are going, I mean, what I'm reporting to you is as we speak, we are working on, so this is ongoing projects that we are working on. In terms of what we are doing right now, we are trying to also start adding the engineering feature to it. Not only the slope, not only the rainfall, but the land use, impervious portion of it. What are the configuration of the elements on the land use, land cover there? And we also try to use other techniques, advanced models, neural networks, random forests. We're trying to find other machine learning techniques to see which one would be even better than the GRB models. And we try to also validate across location, at different location, try to test it and validate it. So we are going to leave India and come to New York City. And New York City, the last few years, everybody has noticed the large urban flooding issue, and we call it flash floods, which is much more significant than the general flooding because it happens quickly in 30 minutes, and people are being suddenly exposed to sudden rise of the water. So we're trying to do something about it. And as you can see from this slide, in New York City, frequency of flash floods are going up. Vulnerability to flash floods, both in terms of poor drainage area as well as the infrastructure that exists in the urban area, and also the weather patterns that has been changing in the last few years significantly make New York City neighborhood, especially those that they are underserved communities, they are very vulnerable to flash floods. And the damages is to houses, to business, to transportation, to critical infrastructure in New York. So it's not just only the people that they want to go to work, but also business are going to be severely damaged, and the infrastructure. So our objective in that project is really try to find a accurate machine learning model to simulate and predict the flood events in New York City, especially flash floods. For those of you that you are not that familiar with New York City is about 300 square miles. Uh, Annual basis, we get on the average about 50 inches of rainfall, which is significant. Temperature is between 3 and 85 on the average. Yes, during some month of January, we might go below 30, but on the general is between 3 and 30 degree and 85 degree. And these are, as you can see, the majority is red, which is the development, medium intensity and high density populations. So it's mostly developed areas. There are not that much land, and so it's a highly populated area. Here, the data set that we have is rainfall. We use the rainfall from 2022 to 2024. The source of the data that we have is one is from NOAA. The other one, we have about 23 weather stations in New York City distributed, and those are being augmented by another 13 from other places such as the NOAA and also University of Albany, that they have distribution network here. So we're using about 30 rain gauges in New York City for those records. The slope, we have the slope of the, and as you see, most of the areas are pretty much kind of flat, 0% degree, but there are areas that they are start becoming orange and red, that they are sleepy slope. And then we have the catchment basins. There is anybody who has been in New York City, you have seen all this catchment basin, which is supposed to collect the runoff. And this one, we get the data from New York City Department of Environmental Protection Agency, and we have about 151,000 catch basin in New York City. And this is all the dots are showing the locations. And then this is zooming on one area. You can see the catch basins. And finally, we have something called FloodNet. FloodNet is sensors in the field that it has been installed to measure the depth of flood in New York City when there is a flood event. We have about 255 FloodNet sensors as we speak today in New York City, that they are active and they are sending the data, and we are collecting those data. The goal is to increase this one to hopefully become 1,000 FloodNet sensors in New York City. So we have a good sense of the rainfall, which is coming down, and the flood, which is measuring the flood. So for this study, we use the date between 2022 and 2024. And this is the methodology that we use. We look at the rainfalls and catch basin and flood depths. We do the processing of the data, we analyze data, and then we start going to classify the floods and test different models. The four machine learning models that we use here are mentioned here. And then at the end, we identify the best one, and then come back here, and for one of the hurricanes that happened in 2023, Ophelia, we tried to forecast it to see if it was doing a good job or not. This is the result of the comparison. As I said, there are four different types here. At the bottom, you can see SVM, RF, LSTM, and XG boost. These are different machine learning techniques that we use, and we try to do an analysis on both in cross-validation, overall accuracy, precision scores, and recall score, and F1 score. These are all statistical parameters that tells you how good is your forecasting and which model does a better job. And you can see the black one, which is LSTM, stands out. And we came to the conclusion that at this point, LSTM is the best model to we used for flood forecasting, flash flood forecasting in New York City. And then we use that one to flood map for Ophelia hurricane that came here. And you can see here we ranked the flood area from yellow 1 to red 5. So when Ophelia came at 1, it's very low ranking floods, flash floods, which is mostly upper Manhattan and lower this part of the Manhattan around the Central Park area. Start getting orange and red, and the red become the highly high in flood map in terms of ranking. Not only that one, not only that we can create a map of like this one, which might be good for some for some agencies, but we are going into the street level flood map. And if you can zoom on this one, you can see two of areas have been zoomed to show the street level map, which street are being flooded and how badly are they getting flooded. So the red one is obviously the rank 5, and the yellow ones, I mean, here you can see that some street that they are yellow, which is very low flood, but then some streets are becoming orange and red. So this is a very good tool for agencies to look at the street level flooding and which streets are being flooded and which streets are becoming mildly flooded, so they don't have to worry about it. So our conclusion on this one is that we can get with minimal input, rainfall, slope, catch basin information, some accurate flood predictions, and of all the 4 models that have been investigated, LSTM machine learning was the best one performed here, and we were able to map the flood risk at the street level and neighborhood level. Now, what are we working on right now is model refinement. We're trying to refine the models, use other type of data, the hybrid models. We use to do the more validation and testing of the different events and time period to see how robust is our techniques, and also start exploring to overimpose or superimpose the socioeconomic impacts on the floods. So, for example, when you see the map of the street level, you see which neighborhoods are poorer, or which neighborhoods are elderly, or which street they have less way of dealing with the floods. Now we are start traveling, going to the south, to Caribbean. In Puerto Rico, there is a lot of flood map, but there is also the issue of the Puerto Rico is very spread. There is a San Juan, which is a city, but there is also local communities around the islands that they need some sort of warning system. So for Puerto Rico, our technique is a little bit different. We try to find the depth, duration, frequency curves, or sometimes they call it intensity, duration, frequency curve. These are design rainfall. When you are designing a road, a building code, or construction, you go with the design rainfall, not the rainfall today or tomorrow. So based on that one, we try to develop a depth, duration, frequency curve that we use a lot of hydrological modeling and train to come up with the map for different period of it. But the key elements of all of these is that DDF analysis, DDF curve. So we try to use a lot of radar data, evaluate the performance of different radar. There are some radars that NOAA facility has there on the islands, and these are for different rainfall events that they are some of them are total precipitation, some of them are 1 hour precipitation, and different format. And then there is USGS, United States Geological Survey. They have rain gauges and rivers gauges that gives us some flooding information that we use those to develop the better techniques of developing a DDF curve. And we want to do it for different durations from 2 years, 2 days to 60 days events. And also we want to do it for 1 kilometer resolution rather than just one for the whole island. So our Flow models are, we look at the watersheds, we look at the input data, which is historical data from radar, from known NEXTRAD data. We use USGS elevation models data. We use from USDA the soil characteristics, and again from known we use land use, land cover maps. These are our input data, and then we try to come up with a flood extent map here at the bottom. But what do we do with the data? We do a lot of analysis of the next rat to develop a DDF curves at 1 kilometer resolution, which is very uh, good grid system and resolution that can help the community as well as agencies. So we focus on radar data to develop the DF curves, because there is the rain gauges are not that many, but there are a lot of radar data that we have. We have rain gauges in Puerto Rico from 2018 till present, and 84 rain gauges we have in Puerto Rico and 2 rain gauges in U.S. Virgin Island. Those are in ground truthing, but then we have NEXTRAD data. These are all NOAA data that we have from 2002 till present at different frequency. And then we try to use rain gauge and radar since 2018 to 2023. So we're looking at this 5-year period to design and develop our model and calibrate our model. When we did that one, we did a lot of evaluation metrics. Every time that you use machine learning or AI, you got to have a way of evaluating the accuracy and the error associated with that one. So we looking at the Pearson correlation, we look at the root mean square error and the percentage of the bias. And if you look at this, the average evaluation criteria for all these 3-4 techniques that we use, you can see the N1P, which is the 1 over precipitation radar, stands out. So we kind of find that the N1B radar product is the best one to be used to develop the DDF curve for Puerto Rico. After that, we start developing also the annual maximum calculation, because the DDF curve is based on different return period. We also wanted to find the annual maximum, so we did a lot of analysis on the precipitation, looking at the two hours to all the 24-hour period, and also daily from 2 days to 60 days on 1 kilometer resolution, and 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 then we did a lot of best fit distribution to analyze and to be able to find which one in terms of methodology was the best one. And we calculated the AIC, used AIC to calculate the errors, best fitting distribution, and then we used two. One was Gumbel distribution, the other one was generalized, generalized extremes values GEV to find out which one. Now you look at the map of the Puerto Rico here. The red one are the Gumbel distribution, and the blue one are the GEV, generalized extreme values. And you can see predominantly the Gumbel distribution for Puerto Rico is the dominant distribution of the rainfall. And we use the radar data, knowing now that the Gumbel is more the predominant one, to come up with the DEF curve. And here is the DDF curve, which is depth, duration, frequency curve. In some hydrological book, they also call intensity, duration, frequency curve, but this one is the depth of it. And you use the Gumbel, you can see we have been able to develop on a 1 kilometer by 1 kilometer grid point for Puerto Rico any period, return period from 2 year to 100 year, 1000 year, a DDF curve, which basically on different rainfall duration. If tomorrow there's going to be rainfall duration of 2 hours, you can go here and 2 hours, 24 hours, It's 1 day, 2 days, and then you can read your expected design rainfall, and that will is going to get an input into the last part, which is the flood mapping part, and that's what we are doing next. Is really getting the, now that we have the DDFK for Puerto Rico, we're trying to input that one into the models to develop the flood map. And the last topic that I want to is the solution. Now we are start getting a handle of rainfall, floods, where the floods are taking place, and how are we going to deal with it. So we try to develop a community-driven decision support framework for creation of nature-based flooding mitigation, especially in Puerto Rico. Puerto Rico and most of the Caribbean, the governmental agencies, in terms of controlling and helping mitigations, they don't have the resources, and there are a lot of underserved community that have been exposed to those things. So we're trying to find a tool that the community also can find out what solution they can be. And we have been in some of those community, and we know they are very active if somebody gives them the tool, the right tool to deal with it. So in this one, the goal, the objective is to develop an interactive decision support model that recommends optimal community-driven nature-based solution for mitigating the floods for different flood scenario. In the previous research, we don't going to map the floods, but now what's the solution to it? So this one is all the black one down here are the source of data that we um, we are using, and then we are in the middle one are what we are trying to do with the data sources. For example, we get the social vulnerability index, the age, disability, low income, unemployment, lack of education. All of those goes into creation of the social vulnerability index map. And there are so many of them out there, but we try to use some of those into our study. And then from FEMA, we look at the social vulnerability map for flood hazards. There are FEMA has created, and some other agency they created some maps of flood hazards. We're doing a literature review. We're going to get using some of the FEMAs, and we're going to do a lot of survey in the field with the community to see what is applicable to those community. One solution to one community might not be useful or doable for another community. So we get some feedback from a stakeholder, and based on the land use, land cover, and slope and drainage, and depth of flood that we use in the models, we come up on the top. These are those circle ones up there. We're going to create the social vulnerability map. We're going to identify the hot spots of Puerto Rico and Virgin Island. We identify the nature-based solution which is appropriate for Puerto Rico. We engage stakeholders and community in seeing which one they are more adaptable to, or it's more acceptable to the community. And then we create what we call it CNBS, a community nature-based solution for suitability. And then we're going to assess it. We're going to see if it's going to be working and how good is it. If it is not good, it's going to go back. If it's less than 20% mitigation threshold, if it's going to go back and then revise the community nature-based solution, and to finally get to the point that at least 20% mitigation is we can use, we can accept, and then go create um, an index map. Index map is going to go into a model which is going to be a decision support tool. So a community in Puerto Rico that they are expecting a rainfall tomorrow, they're going to look at at an app that to say, okay, there is going to be a rainfall, and this rainfall is classified as that, and the model is going to do all these things, and at the end, they give them the options, what option they can use to mitigate the flooding there. Now, in this project research, we look at the social vulnerability index and identification of hotspots. So there are a lot of social vulnerability index. Some of those are relevant to what the flooding one. We identify those and like status, household characteristics, the age of the people, the type of the households, and we put those things into one, and we try to identify the hotspot in Puerto Rico. And here is the outcome of that table that you see. So here we use social vulnerability index, which is out there, and then we look at the normalized flood frequency that has happened in Puerto Rico in the past, and also flow accumulations that has been because of mostly poor drainage system. And then we combine those things, and these are the coastal floodings that are happening. And then at the end, we come up with the composite flood vulnerability index. Now, you're looking at this one, you can tell which communities in which part of the Puerto Rico are more vulnerable to flooding, and in association with the ages, in association with the social vulnerability. So we combine these two, so flood plus social vulnerability, to identify what we call them hotspots that we have to deal with it. After the hotspot is created, see, um, now we have we are trying to develop the nature-based solution. Now, FEMA is suggesting some nature-based solution on the left column here. There are 6 of them. Uh, Building dunes, bioretention system, permeability pavements, rainfall harvesting, bioengineering, riprapping, or stream bank stabilization. But there are other parts that we are adding to it because they are nature-based solution, but they should be considered. For example, mangrove restoration, constructed wetlands, green roofs, shoreline stabilization using living shoreline techniques. So we're trying to combine what the FEMA is suggesting and some which makes sense for Puerto Rico and doable, and we try to right now we are at that stage that we are combining the stakeholders, and then we're going to survey the communities. Survey actually next week. 2 of my PhD students are that one is looking at the flood forecasting, the other one is mitigation strategy, going to Puerto Rico to survey, to identify communities, and also looking at communities and to see in Puerto Rico there are 7 municipalities, so they're going to go and then start um, understanding the situation, but also understanding which one is suitable for the community there. And then we weight them from up to 10 of the natural-based solution that they can identify. So depending on the rainfall that might be happening tomorrow, they can pick one of those for their community. Now, in terms of the flood mapping, right now this project we're using Geisha and a number of other methods that there are HEC-RAS and HEC-MS and all SWIM and SWOT models to develop the flooding zones. And these models we use to mimic the natural system and simulate their impact, while our flood models are going to come into the line because they're doing parallel things. So one of those 5 is going to be replaced with one of the flood models that I just mentioned before. And then we're going to create a community nature-based solution with performance index, that which one is for which community would be better from 1 to 10, so they can choose and pick based on the community. And then we're going to, at the end of it's going to be a decision support model. It's going to be a model that the community they don't have to run, they just look at the input and they put the input and they get the output and they choose the type of solution that they are envisioning. Last 2 slides, I just want to mention that we have some data products. Puerto Rico very engaged. So there are WRF-based model that we have run. We can forecast precipitation the 2.8 kilometer resolution for Puerto Rico, and we can do it for different time periods: 0, 6 hours, 12 hours, 18-hour cycle, up 24-hour cycle. So 24 hours before the rainfall comes, we can forecast the precipitation estimation of 2.8 kilometers. Now, new ones that we just talked about it, we're using AI. Now we are downscaling to 1 kilometer. So basically, 24 hours in advance on 1 kilometer resolution, we can predict the precipitation that's coming in Puerto Rico. And this is another product that we have. There is Puerto Rico being a lot of slippery slope type topography. There's a lot of application of the rainfall that we use. One of them is landslide susceptibility. This is the map that shows the from the very low, from light green to red, which is very high, areas that they are susceptible to landslides. And this is just showing for the Hurricane Maria that was generated, but we can do that for the next 24 hours. This is operational product that they can give the warning in terms of the potential landslides. And also in terms of the preliminary result of the flooding, this is west of Puerto Rico. These are three communities, and shows the level of flooding in millimeters. And the red is about 4 meter at the outlets. Severe storms, a lot of them are in the order of, the smaller scales. The yellow one is 1 meter floods, and this is going to be extended to the entire island. As you can see, this is only three municipality on the west coast. And with that, I went a little bit over the 35 minutes that I was told, but I apologize. So if there is any question, I would be happy to respond.
Thank you so much, Professor Khanbilvardi, and that was perfect. You didn't go over anything at all. We appreciate the time to have questions. Just to start us off, I guess I'm wondering if you could talk a little bit about what strategies you use to ensure the long-term sustainability of these tools, especially in under-resourced communities or when funding to organizations like NOAA is being cut. How do you make sure that these tools are able to be continually used by communities?
Okay. It's two level of sustainability issue. In large cities, you have to convince the agencies to be able to use the product that you come up with. And that only you can show that, but with a lot of examples of different events and things. So we are, in New York City, we are working with Department of Transportation to show them street level mapping of the flash floods are being useful for trucks and traffics. Try to at least give them, I apologize for the lights, because after, if I don't move my chairs, it's going to go off. But anyway, so that's the thing. But in Puerto Rico, what is different, because we're working with the community, because the central governments, they don't have the resources. When they don't have the resources, you have to pull in the communities. When they have resources, such as New York City or Bombay, you have to bring in the government and the agencies. So in Puerto Rico and Caribbean, we're creating something called Community Flood Mapper. This is an app that we have created on that community. They can go outside when there is a flood. They can take a picture of it and then upload it. We know the location on the GPS, and we know and there's some information about depth of flood. Is it knee high or toe high, or how long they have the flooding, 1 hour or 2 hour, and those output from the community is going to ingest into our model to calibrate and validate the model. So a strategy for sustainability, we think the best way to make it into the app, because nobody except us is going to sit down behind the computer and run the model. If we develop apps, it's become much easier for community to use it, and we're going to have a workshop for the community to tell them how to use the apps, and that potentially would be the source of sustainability.
Okay. Thank you so much for the insightful presentation. And I will ask a question regarding Mumbai. I know that in developing cities, informality is a major issue, and most of the infrastructure are aged, or some are aging. How have you factored this into the model, and how is human behavior a major issue in your modeling?
There was a lot of echo. What was the first part of your question? I didn't understand it clearly.
Informality and aging infrastructure in developing cities. How have you factored that in the modeling?
Well, at this point, I mean, right now we are working with the National Institute of Disaster Management in Puerto Rico, in India. As you might know, getting the data in the local infrastructure data is hard for us to get it. So we are collaborating with some of the faculty at the university level there, at the also the National Institute for Disaster Management. Actually, the PhD student that's working with us is coming from that agency to work with that one. So that's becoming easier to get the data and also input the data. Now, in terms of infrastructure, it is a challenging one. Even in New York City, for example, New York City, the drainage network in New York City, DEP does not want to give it out for security reasons. So we have to use the outlets and then some estimation. So we going to use as much information as we can, but I mean, still there would be some that we might not be able to get a hold of it, but we see how it goes. But the goal is to not only look at the slope, but as I said, on the ongoing, to look at the land use, land cover, and infrastructure.
Well, thank you, Doctor, for the informative presentation. My question is about in fragile urban areas where infrastructure is usually weak. Sewage often mixed with stormwater. Can this AI predictive model still be effective, from your opinion?
Say it again. I mean, the AI model be effective in what?
In prediction of the flooding, in
Yeah,
case
I mean,
or integration of the sewage mixing with the stormwater. This will add another hazard.
correct. I give you the example of New York City. New York City, about 75% of the drainage, what we call is the combined sewage system, which it means when there is a rainfall and flooding, they overtake the sewer system connections. So basically, they go to treatment plants, and so it overloads the treatment plants. So at this point, it is it is a challenging to kind of identify what percentage of what community goes to combined sewer, which one doesn't. So it's a challenging issue when you bring the the sanitary sewer system into the system, because a lot of municipality, they have only one system of drainage, the outlet to the river. So the best way is what we're looking at the street level drainage system to see how many manholes are there and where are they exactly located. And that one we know because these are on the surface. And also identify the sink source of each one. For example, for each one, how much flow that can take, the size of it is identified, but also find out the queue that goes into it. So basically take that part into consideration. Now, I acknowledge that there are other elements that might cause flooding that might not be in our model. For example, if a street, if cleaning is not done and the drainage network is clogged because of the newspaper or plastic or debris, this is going to cause, in some areas, going to cause flooding that our model cannot predict that one because we don't know if it has been clogged or not. And so surface maintenance of the drainage system is another challenging issue that is going to be another factors in sometimes over prediction or under predictions. But we got to start from somewhere. Get the models, run the models, provide a tool such as the apps that people can see it. I was always telling my team that everybody use Google Map and was for traffic. Where is the congestion of traffic? We want to develop what they call waterways. That basically a map that shows which street is being flooded at what level. So if somebody wants to go home, they can take a look at it. And in addition to traffic, also look at consider the flooding areas that they can avoid.
All right, thank you, Reza. I'm just curious. I know a lot of people in these days are leveraging AI to develop flood warning systems. So your university developing one. I know New York University is also there, NYU is also there. So scientists everywhere, especially in New York City, and even some private sector, universities are also working on this. So I'm just curious, has this been done in silence or you are trying to integrate? Because if the end users will be the government, at some point, they will have to make a decision which of the flood warning system is actually the best, for us to pick from and things like that. Have you considered that at all in your work, especially as you progress?
Well, integration of different universities, you understand New York City, they have a number of well-established university with research capabilities. New York City is trying to, they have what they call a climate committee that they look at different extreme events and how to coordinate between all these university and research and then combine them. In terms of individual two faculty from two university working together, it's not happening, but the data collection and data sampling. For example, when I mentioned in New York City, there is a flood net. It's between City University of New York and NYU, and that they have invested in these sensors to put the sensor in the field. So both universities are using the same data. But in terms of the AI developments, as you know, there are many different AI approach and models, and how you integrate and come up with the better solution, which one is fit for Bombay, which one is fit for New York City, is something that the research at different campuses. There is not that much coordination in that part. There are coordination in data, collecting data and sharing the data, but there are not that much coordination. Is all the hydrologists from the private industry, from the governmental agencies, and also from universities sit together and say, there are some conferences and events that are happening, that people, they share their result, but that's as much as the integration, not really working together in developing one model. But sometimes during those events, the opportunity comes that you can start collaborating with somebody in NYU. I mean, I have good colleagues of mine in NYU that they're working on it, but our methods might be different also. It's a challenging one. That can we have one group of hydrologists in New York City to work on the flooding issue alone? It's also the competition that, everybody try to come up with a better model, better approach, more useful to communities.
Thank you so much.
Yeah, thanks, Mario. Thanks, Professor Reza. Very nice presentation, and you covered a lot.
Thank you so much.
Also, you have an experience of implementing or researching on this from Mumbai to Puerto Rico to Caribbean and New York. So can you say that if something you work on, because urban flooding research is very data intensive and you don't have all the data available for all the cities. If if someone wants to develop things to a city in another country, in the developing countries, what would be like optimal method that you think that can be how considering the limited availability of data? So because New York has a lot of data, I know, but you don't have same data in other countries, in other cities. So what would be your approach or recommendation?
Well, I mean, if you notice at the beginning of my presentation, the last item was transferable. That we like these solutions not to be dedicated to one particular locations. Actually, there is a lot of transferable between New York City and Mumbai. Whatever we learn from New York City, because it's not highly populated, but we have a lot of data. We have a lot of rain gauges, we have a lot of radars, we have a lot of information about the floods, and those are not there in Mumbai. So we're trying to use some of those lesson learned from New York City and apply it to Bombay. So, for example, in Bombay, for example, we found a gap in data. We say, okay, we can find satellite data to fill the gap. That the gap doesn't exist in New York City. So at the end, the models that comes out, even though they might be site specific. For example, we use 4 models for New York City, and we found one which is very fitting very well. Those 4 can be used in other large cities to see if the technique can be transferable and the model can be used there. For example, when we develop our model at the end, this can be used for, let's say, New Delhi. And then we have to have some data for New Delhi that we can, because all these models, they need calibration and validation, and then we can, get those things. Now, if there is there is an urban area, let's say in Africa, in Kenya, that they don't have the data to calibrate and things, then we have to find alternative source, such as models, such as maybe only some satellites and some assumption to develop some basic data to run the model with, because eventually it it will require some input into the data, into the models, but they can use the models. I mean, we have been fortunate in the literature to look at some of the models that have been used in other countries like Japan and China and Europe, and we try to pick those to see if they work in New York City or not.
Thank you.
Thank you so much, Professor. We have more questions, but unfortunately we don't have any more time. We thank you so much for your very important work, and congratulations both for the work that you're doing and the future work at the Hub. Thank you for taking the time to be with us, and thank you all of those who joined us online. We hope you all keep well, and we will see you next week.
Thank you very much. Have a good day.